Otherwise, it won't record the audio when I record this thing. All right, so you're just being introduced to exponential functions, right?
Yeah.
All right, well, let's talk about your most basic exponential function.
Hey, Mom, could you clean this? Could you clean my glasses, please? Thanks. Okay, sorry.
In other words, the parent function to number 1 is y equals 2 to the x.
Yeah.
Okay? Well, if I graph that, all exponential functions tend to look similar. They all kind of look like that. And whether it's 2 to the x, 3 to the x, or 117 to the x, they all cross the y-axis at the same point, 0, 1. Notice that when you take any number to the 0 power, it's equal to 1. So 17 to the 0 power is also 1.
Yeah.
This chart, or this graph right there, which is y equals 2 to the x, looks like that. Well, if I said, well, what does y equal 15 to the x look like? It's going to be similar. It's going to go through that same point. It's just going to go up a little quicker like that.
Right.
Because 15 to the x is going to increase faster than 2 to the x would. But if I just drew the chart and didn't tell you which one it was, you'd have a hard time telling me which one it was. So know that about exponential functions, is that they all tend to look the same, but that they all go through this same point. Now, using that information and transformations, we can graph this one that they gave you. First of all, let's talk about the transformations. What's the consequence of the 5? What is that, 5? It's a vertical stretch factor.
Right, yeah. So that would, like...
If I were to vertically stretch this graph I've drawn over here, it just means that every point is 5 times further away. So if I vertically stretch this graph, I get something like that. In other words, this graph here might be y equal 5 times 2 to the x. In other words, if I had a point there, that point is now 5 times further away from the x-axis. So when I say a vertical stretch factor on an exponential function, it just means it gets steeper quicker.
Yeah, that makes sense.
Okay, so we got, let me write these because we got a bunch of them. They started you right off with one that's got 3 things going on. So it's a vertical stretch by a factor of 5. What's the consequences of this minus 2 in the exponent?
Wouldn't that make it, I'm not sure. What would that do?
Well, this is a little tough to see in exponential functions, and a little tough to explain. Let me go back to my original parent function and call it f of x.
Okay.
So f of x is equal to 2 to the x. Well, what would f of x minus 2 be?
0.
It'd be 2 to the x minus 2.
Oh.
In other words, you take whatever's in the parentheses and you substitute it for x. So that's what we're looking at, is 2 to the x minus 2, which means it's f of x minus 2, and when I write it like this, that is a horizontal shift to the right of 2 units.
So basically it shifts it to the right opposite of the side.
Yes. If that was a plus 2, it would be to the left by 2 units. The key thing is it's a horizontal shift. It's not a vertical shift. It's not a horizontal stretch or shrink. It's a horizontal shift. Everything horizontal is inside the parentheses. Everything vertical is outside the parentheses. That's the best way to remember it, as far as I know. Okay? So I want to draw these one at a time, because if I draw all three of the transformations, it's not as easy to see. Okay? So in green, I'm going to do this one. Well, the way I would shift this black line, in other words, this is 2 to the x, but I want to graph 2 to the x minus 2. Well, I take this one known point and I shift it 2 units to the right. So 2 units to the right makes that point 2, 1. And now that curve would look like that. So the green curve would be y equal 2 to the x minus 2. With me?
Yeah.
Okay. Now let's take the third, minus 2. What's the consequences of that minus 2?
Would it take you like down 2?
Yeah, it's vertical because it's outside the function being 2 to the x. So you know it's vertical, just like the 5 is a vertical adjustment because it's outside the function. But the minus 2 merely takes this new point and moves it down 2 units, which puts it at 2, minus 1. Let's do this in red. So this curve here is now y equals 2 to the x minus 2 minus 2. And now the only thing left to do is to apply the 5. And I'll do that in blue. Well, remember the 5 does not affect this point right here. It's still going to go through that point. It's just going to be 5 times further away from the x-axis. Something like that. Like what you've drawn. What you've drawn works pretty good. Let's make sure, though, that we get the y-intercept proper. Notice that the only point I worked with was this original 0, 1. And I moved it either to the right or down. And then when you're doing stretches, they change the shape of the function as opposed to shifts, which do not. When you're doing a horizontal or a vertical shift, you're taking the exact same, the shape of the function and either moving it up or down or right or left. When you're doing stretches or shrinks, you actually change the shape of the function. So if I want to know, let me point with my cursor, if I want to know where that y-intercept is, in other words, 2 nice points to know on your curve would be the y-intercept and the x-intercept. How do I get the y-intercept from the function algebraically? In other words, forget about transformations. Let's just look at it. What's x when I'm talking about the y-intercept?
X is what you're solving for?
X is 0, right? Isn't x always 0 when you're talking about the y-intercept?
Yeah.
Okay, so if this is my function, set x equal to 0, and let's figure out what that number is. So I get 5 times 2 to the negative 2 minus 2. So what's that? 5 times 1 over 2 squared minus 2. That's 5/4 minus 2, which is equal to negative 3/4. So that point, yeah, you crossed it absolutely perfectly. At some point you must have figured that out, how to figure out the y-intercept.
The graphing function, she's letting us use her calculator.
Oh, you're kidding. What's her point of asking you to graph it if she lets you use your calculator? That just means you're going to use your calculator and then copy whatever's on your calculator onto that graph, right?
Yeah, that's what he likes with graphing.
Oh, so he's not really expecting you to do this in terms of transformations.
No, he's like, he sort of like understand it, like maybe not for the specific function, like the specific thing, but like you'll like get the meaning of it.
This seemed like an overly difficult problem to start out with if they wanted you to do it using transformations, because it's got three things going on. That 5 does something, the -2 does something, and this -2 does something else. So this is a difficult problem if I'm trying to teach you how to graph this function based on transformations. I would not start out with something so difficult. I would take one of these things at a time and try to do it.
Yeah,
but
some of the other stuff that's going to be on the test, but is like compound interest and exponential. Like.
All right. So maybe we should bypass these and go to those. Because if he's letting you use your calculator, I don't know the purpose of the problem, other than to be able to make sure you know how to input that function properly into your calculator.
Yeah.
This one, incidentally, is not correct. Well, unless that dotted, yes it is, sorry. I was thinking your dotted line was the x-axis. It's not. Your x-axis is the bottom line, and it's definitely shifted up 2 units. So this one looks correct also. But yeah, if we're not going to do those as transformations, there's no real point in talking about them. Let's go down and do these solve each equation. Or what's this stuff up here? This is your exponential growth and decay.
He didn't give us a worksheet on it, but like we did it in class. Like we have like exponential. He expects us to know about exponential growth and decay. Like,
okay.
Those functions.
Let's talk about that if we have time at the end of our session. Let's look at these 7 through 12, because these are pure algebra problems here. And then we'll go back and we'll talk about your exponential growth and your exponential decay.
And we also have like probability on our thing, but I know you don't really do that. So.
Well, I do simple probability. I probably can handle your probability that you're getting now. In other words, if you have 6 red balls in a jar and 5 green balls in a jar, and you pick a ball at random, the odds that it'll be green are 5/11ths.
Yeah.
So I can do your basic probability. It's just that when you take a course that's strictly probability and stats, you get into a lot harder probability problems that I don't do enough probability and stats to do. So let's talk about these. Now, normally, in order to solve an exponential equation, first of all, exponential equations differ from algebraic equations. This is not an algebraic equation. You cannot use algebra to solve it. Well, in this case you can, but typically you wouldn't be able to. Typically you would have to use logs to solve an exponential equation.
We didn't learn that, so.
I know, and that's why all of these problems are of the same nature, as you haven't learned logs yet. So the secret to solving these exponential equations is to find a common exponential base. In problem number 7, what is the common exponential base between the numbers 3 and 27?
3.
Okay, so I can rewrite this as this. I'm going to, instead of writing 27 as 27, I'm going to make it 3 cubed. Now, notice how I can solve that problem. If I've got 3 to some exponent equals 3 to a different exponent, I can equate the exponents.
Yeah.
Negative x plus 1 equals 3. Now you get the answer. X equals minus 2. So these are pretty easy if they have common exponential bases, which all of these are going to have, because otherwise you'd have to use logarithms. In other words, if I said 3 to the x equals 26, cannot solve that without using logs. There's no common exponential base. If I said 3 to the x equals 18, I cannot solve that. There is no common exponential base. So a common exponential base means I need to be able to write this number in terms of 3 to some power. So if it was 3 to the x equals 81, well, I can write 81 as 3 to the 4th power, so x would have to be 4.
Right.
So the secret on all of these is going to be to rewrite them with a common exponential base. Well, on number 8, what's the common exponential base between the numbers 625 and 125?
5.
Yeah, so how would I write 625? I'll just go straight into it.
625 would be 5 to the 4th.
Okay, so it's going to be 5 to the 4th, and make sure you put that in parentheses like that every time. Every time you need the parentheses, because this number is not the same if I don't use the parentheses.
Right.
How do I write 125 in terms of 5?
5 to the 3rd.
Again, in parentheses, and then that whole thing is going to go to n plus 3. Now use your rules of exponents. What's the left side equal to?
What?
Use the rules of exponents. What we have going on here is double exponentiation.
Right.
When you have double exponentiation, you're going to multiply the exponents. So multiply 4 times this exponent. What do you get?
Let's see, 12, negative 12 then, minus 4.
Uh-huh. And on the other side, multiply the exponents.
3n plus 9.
And again, we have the same base to one exponent equals the same base to a different exponent. You can equate the exponents. Once you get it to that point, you can always let the exponents equal one another. And then that's just an algebra problem there. In other words, 15n equals minus 13. So n what do you, I didn't hear that last part. What'd you say?
The way I did it is I just put the exponent as like on the outside of the parentheses, and then I put like the exponent in parentheses, like so that the exponent like 5 to the 4th like power would go outside the parentheses, and we distribute it.
Well, technically that's the same thing.
Really?
Well, yeah, notice how I did this. This is double exponentiation, and I multiplied the exponents. That's the same as taking that 4 outside and putting a parentheses around that. That's what you're doing, is multiplying the exponents. So you're doing it the same way, but it's not as understandable. In other words, if I were to say, what is this number? 2 to the 3 times 1 plus 4.
Yeah.
That's the way you're doing it, right? That's the same as 2 cubed to the 1 plus 4 power. In other words, what you're really doing is double exponentiation, and that calls for multiplying the exponents together.
Okay.
So either way, you get 2 to the 15th. In either way you do it. But I think it's important to stick with your rules of exponents. And by that I mean this. Here's your 3 rules of exponents. There's rule number 1. Here's rule number 2. And here's rule number 3, where you have double exponentiation, and that's equal to b to the xy. So it's all you're doing is jumping straight to that step when you do it your way. But it's important to know that the way you get to this step is the fact that you had a double exponentiation problem to begin with.
Yes.
Okay. So number 9. What's the common exponential base between 64 and 1/16?
8.
Actually not. You cannot write 16 as an exponential of 8. It's not 8 to the 1 power. It's not 8 to the 2 power. How about 4? I can write 64 in terms of 4, and I can write 1/16 in terms of 4. What's 64 in terms of 4?
To the 3rd.
Yeah. And so the left-hand side of the equation becomes this. That's why it's important to think of this as double exponentiation, because that's step 2. Now, how can I write 1/16 in terms of 4?
You could put like negative.
It's 4 to the negative 2. 4 to the negative 2 is the same as 1 over 4 to the positive 2, which is 1/16. So there's your 1/16. Now I got to take it to the x plus 3. So, well, now I'm going to multiply exponents. In other words, now I've got my common exponential base on both sides of the equation. It's 4. So what's the next line?
You multiply the exponential.
So give me the next line. Do that.
The next, do you mean like the next step?
Yeah, how do I go to the next step from this? In other words, you can't do anything until you can do something with these exponents.
Double exponentiation.
So what's the next line on the left?
Multiply them.
Uh-huh. What do you get?
You get negative 3x.
No. What's 3 times minus 2x minus 1?
Minus 6x minus 3. And, sorry, it's coming.
What's on the right side?
Negative 2x minus 6.
Okay. Now I've got same base, and I can equate the exponents. So it's the same process every single time. Get those bases to be the same, and then you have a simple algebraic solution. Do you want to go, you want me to take this all the way to the solution, or do you know what to do from this point?
No.
Don't need to spend any time on solving this?
No, I can solve that.
Good. Okay, let's go to the next one. We got 64 to the a plus 1 equals 1/2 to the a. What's the common exponential base?
2.
Okay, tell me what the next line would be.
It would be 2 times 2 equals 4.
Hold it. 2 to the what?
I'm trying to figure out the...
How do you write 64 in terms of an exponential base of 2?
Would it be...
2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. 2 to the 6th is 64.
Okay.
So that's 64 right there. It's to the same exponent. How do I write 1/2 in terms of 2?
You go like negative 2 to the second, right?
No.
Or 2 minus to the negative second.
There it's 2 to the minus 1.
Oh.
In parentheses. The parentheses are very important here. And the reason they are is because if I write this, that's not the same as 3 cubed cubed. In other words, if I don't write the exponents here, if I don't put parentheses around this part here, it's a totally different number, and by a huge amount. You know what this number is right here that I've written?
Yeah.
That's like 10 trillion. Because the first thing I'm going to do is 3 cubed, so it's really 3 to the 27th power, which is a gigantic number. Whereas if I do this, now I take 27 to the 3rd power, which is nowhere near as big. So these parentheses are absolutely vital. Some parentheses are just for display, others you have to have. Now, what's the next line?
2 to the 6a plus 1 equals to the negative a.
No, I'm multiplying 6 times the a and the 1.
Well, 2 to the 6a plus 6.
Okay. Equals
negative a.
Well, it equals 2 to the negative a. Okay, now I got my same bases, equate exponents. What's the next line?
6a plus 6 equals negative a.
Okay, and then we'll stop there. I'm going to trust you know how to do those easy enough. All right, let's look at number 11. 216 to the minus a plus 2 equals 1/6. What's the common exponential base here?
6.
Okay, how can I write, what's the next line?
6 times 6 equals 26 times 6.
What's 216 in terms of 6?
6 to the 3rd.
Uh-huh. They're always going to be a small number. In other words, they're not going to give you a problem where this is 6 to the 7th power. Nobody knows what that is without a calculator. How do I write 1/6?
6 to the negative 1.
What's the next line? Using the rules of exponents?
Would be 6 to the negative 3a plus 6.
Equals 6 to the minus 1. What's the next line?
Which you get a by itself.
Well, give me the next line.
Oh yeah, right. You just push the exponents. Like,
You equate the exponents. So the next line is minus 3a plus 6 equals minus 1. Now that's a simple algebra problem you can solve. So the key with all of these is to convert them to algebra problems, because they're not algebra problems to start with, they're exponential problems. But as long as we can find a common exponential base, then we can turn them into algebra problems instead of log problems.
Yeah.
What's my next line here?
Here, it would be 6, here, I'm just erasing what I did.
Do these step by step. Don't try to do 2 steps at once.
It would be 6 to the second, and like negative 3k equals 6 to the negative 2.
Not 2.
Negative 3.
Okay. 6 to the negative 3 is 1 over 216. Because all I'm doing is rewriting this number. That's all you're doing here. Just like I'm rewriting 36 as 6 squared. Okay?
Right.
Doesn't change the exponent. Just gives me a common base. Now apply the rules of exponents. What's the next line?
It's 6 to the negative 6k equals negative 6 to the negative 6 minus 6k.
And the next line?
Negative 6k equals 6. Negative 6. Negative 6k. Negative 6 plus 6k.
Okay. Again, simple algebra problem. End up with 12k equals 6, k equals 1/2.
Right.
Okay. Let's see.
We're working on what's it called? Like exponential growth and like bank stuff.
Okay.
Let me see if I have an example problem sitting there.
Yeah, I know what you're talking about. You're talking about exponential growth or decay?
It's just another thing. It's like with that and like with bank statements and stuff.
Right. When you deposit your money into a bank, it promises to pay you interest at a certain rate per year. And they're going to compound it yearly. And the amount that your money is worth at the end of a period of time is the amount you started with, a sub 0, times 1 plus the rate that they're paying you, all to the t power in years. So let's say you deposited $100 at 5% interest for 3 years. What would it be worth at the end of 3 years? Well, here's how I do it. The amount that it's going to be worth is the A on the left. A sub 0, I started with $100. My interest rate is 5%, which I need to put into decimal format like that. And the time is 3. So this becomes just a number that you can get out of your calculator. 1.05 cubed times 100. Do you have a calculator in front of you? Do that. Make sure you know how to do that in your calculator.
Yeah. I'm just plugging my calculator into the wall real quickly.
Okay.
And it's like, because,
Make sure you know how to exponentiate stuff. Like,
yeah, you just like make it equal to,
well, you do something like this. You do 1.05 raised to the 3 power. And then multiply that whole thing by 100.
Yeah,
Okay, so the final answer is what?
1.8.76.
Like that? In other words, you multiplied it by 100. So your $100 at the end of 3 years would be worth $115.76 if they were paying you 5% compounded annually. Now, there's actually 3 different ways to compound money. There's an infinite number of ways, but there's 3 different formulas. One is if you compound it yearly. The other is if you compound it more frequently than yearly, like monthly or daily. And the third one is if you compound it continuously. Now, I don't know that they've taught you all 3 yet. Is this the only one they've taught you?
No, they taught us all 3.
Okay. Let's talk about the other 2. Let me just write them out. That one there is the general formula if you compound it yearly. And that's what most banks do. Not all. Some will give you a deal and they'll compound it every 3 months. But this one's compounded yearly. If you're compounding it more often, greater than yearly, which means like less frequently, then the formula becomes this. Do you use K or N? What do you use?
Yeah, it doesn't matter.
K is how frequently, how many times a year do you compound it? So let's take the same problem. You're earning 5% per year, but this time with your $100, they're going to compound it every 3 months. So the way I'm going to write that is A equals $100, my starting amount, times 1 plus, there's my rate, my annual rate is 5%, but I'm compounding it 4 times a year, every 3 months. I'm still going to do it over a 3-year period. So whatever this number comes out to be is your answer. And you'll find out that it's slightly more than $115. The first way we did it, where we compounded it yearly, we got $115 and change. This is going to be a little bigger because when you compound more frequently, it grows a little faster. You with me? You see where I got this formula that I've circled? You see exactly how I got it?
Yep, I understand that. Yeah.
Well, what would it be if I took the exact same problem and compounded it monthly? What is it now?
Oh yeah, monthly, right? Okay, you did it quarterly there.
Right, I did it quarterly there, which is 4 times a year. So if I'm doing it monthly, what are these numbers going to be? 1 plus what?
It'll be like divided by 12.
0.05, the same 5%, divided by 12. And then over 3 years, I got to multiply that by 12. That's the hard part to remember, is because that seems like such an enormous exponent. And it is. But notice that I'm taking a very small number to an enormous exponent. 0.05 divided by 12 added to 1 gives you a pretty tiny number. It's just barely bigger than 1. Well, if I take numbers that are barely bigger than 1 and I take them to a giant exponent, they don't grow that much. Do this one in your, do you have your calculator still? Figure out what that number is, take it to the 36th power, and tell me what you get. It's going to be bigger than 115, but not that much bigger. Sam, you still there?
Yeah, I'm here.
Okay. I wasn't sure if I'd lost audio or not.
Just putting it in the calc.
Okay. These can be a little tricky getting into your calculator. That's why I want you to do it, because I want to make sure you know how to do this.
16.15.
What is it?
116.15.
Yeah, notice that that's bigger than we got when we compounded it annually. We only got $115. So the more often that they compound it, the faster it actually grows. Okay? And then there's the third one, which is the way nature works, which is continuous compounding. In other words, the only thing that's compounded yearly or monthly are bank accounts. That is a completely artificial process. It doesn't occur in nature. There's nothing in nature that compounds yearly or monthly. Compounds continuously. That's what nature does. If you have bacteria growing in a petri dish, it's going to compound continuously, and that's equal to this. Instead of 1 plus the interest rate, it's the number E, Euler's constant, to the RT. So take the same exact problem, $100 at 5%, compounded continuously gives you what? Gives you 100 times E to the 0.05 times 3 years. And if you do this one, you'll get something just barely bigger than 116, because continuous compounding is better than monthly compounding, which is better than quarterly compounding, which is better than yearly compounding. But it is a very different looking formula. In other words, the second formula here is very similar to the first. It's just I'm dividing the interest rate by K and I'm multiplying the T by K. But continuous compounding is quite different. And when you have decay, it's always continuous. Nothing decays on a yearly basis, although people will talk about, if you go buy a new car, you'll lose 20% per year in depreciation. Well, that's decay. And sometimes they'll use this first formula to figure out what it's worth at the end of a few years. But in actuality, you should always use that formula, the continuous, because nothing decays yearly. Things always decay continuously. If I give you a piece of uranium-238, it's going to decay continuously. So it's always the third formula. It's a negative rate.
So you just subtract it from one then, pretty much.
No.
You don't know that you're subtracting.
You put a negative in front of it. Let's say we start with $100 and we're going to lose 5% continuously. What's it going to be worth at the end of 3 years? That's my answer. I mean, I have to put it into a calculator, but this is how I would get it. To the minus 0.05, because it's decay, it's not growth.
Right. So for decay, you can just make it negative. Oh, it's always negative rates, right?
Yeah. Now, I'm a little confused because a lot of times they will only teach you the yearly compounding. And at the same time, they will talk about decay, and they will have you use the yearly formula for decay even, which you can do. R is just negative, so I could use this number one formula. But nothing decays annually. Nothing in nature. not even bank accounts. Everything in nature decays continuously. So all decay problems should really be using this formula here. But with students, they don't always start you off with all three formulas. They only start you off with this top one, and yet they still want to talk about decay. So they'll use the top one in talking about decay, like a car depreciating 30% per year. Well, they'll use this one here. Well, a car doesn't depreciate only on December 31st. The car depreciates continually every single day you own it. It depreciates. It may have an annual depreciation of 20%, but I should plug it into that formula right there, not the top one, ever. It's just they teach it that way because they haven't taught you the other two formulas yet. But if they've taught you all three formulas, then every time they talk to you about decay, you should use that third formula, the continuous decay one. Okay? Now, do you have any specific problems regarding these growth and decay?
We did them in class. Those were like not that bad. The thing that I didn't do great on was like card probability, because I didn't really.
Okay, let's talk about some probability. Give me a probability problem.
A dependent card problem about aces or something.
Go ahead, give it to me. We'll do it.
I don't have it written down.
Okay, I'll give you one. What are the odds of drawing an ace from a 52 card deck?
Would it be 4?
Well, it's 4 over 52 because there's 4 aces and there's 52 cards.
So it'd be 1 out of 13, right?
Correct. So simple probability is pretty easy, but probability problems can get way beyond simple, let me tell you. They can be very, very complicated.
They give me could we do one about a 36 side die?
Yeah. 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 Okay.
He doesn't give us back our quizzes, really.
Okay. So what are the odds of rolling double sixes when you roll 2 die?
36,
Well, there's on 1 die, what's the probability of rolling a 6?
1 out of 6?
Yeah, because there's 6 faces and there's only 1 6 on a die, okay? So you have to roll a 6 on 1 die, and you have to roll a 6 on the second die. So it's 1/6 times 1/6, which is 1 over 36. But let's talk about that principle. Let's say the odds that it's going to rain today are 30%, and the odds that it will rain tomorrow are 30%. Well, what are the odds that it's going to rain both days? 0.3 times 0.3. In other words, both things have to occur. It has to rain today and it has to rain tomorrow. So the odds that it would rain both days are actually only 9%. Now, rain isn't really a good one to use because this presumes that these events are independent of one another. Whereas when you're talking about weather, they're really not independent. In other words, if it rains today, it's more likely to rain tomorrow, right? And if it doesn't rain today, we're not in the middle of a storm and it's less likely to rain tomorrow. So you only multiply it if the events are completely independent of one another. For example, let me give you an actual one that is correct. if I flip a coin twice, what's the odds that it will come up heads and then tails exactly?
50 or 25.
25, because the odds of the first one are 50%, and the odds of the second one are 50%. Since they both have to occur in that order, the odds are 25%, or 1/4. There's some really, really cool probability problems that will astound your friends. In fact, we used to have a DVD night with my dad and family, and there were 14 of us in there one night, and I presented this probability problem, and none of the 14 people believed me. I was the only one that I could convince. And here's the problem. If you go into a house and you know there's 2 children in that house, and a kid comes out into the room. Let's say you walk in and the parents are in there, and one child comes out and it's a girl. What are the odds that the other child is a girl? You know they have 2 children. You've looked on the census form and it says there's 2 children living in this house. And you walk in the house and you don't see any of the children, but a child comes out of the bedroom and it's a girl. What's the odds of the other child being a girl? Not 50-50.
It's like
Here's the way it works. Here's how you figure it out. This is a fun problem. This is like the classic probability problem that to amaze your friends. Okay, here's the way two children can be born. You can be born girl-boy. You can be born boy-girl. You can be born boy-boy. And you can be born girl-girl. That's the only possibilities of having 2 children, right? Well, when you see a girl, it eliminates this possibility. They did not have 2 boys. You saw one girl. Well, the odds of the other one being a girl are 1 out of 3. Because there's only 1, 2, 3 possibilities, and only one of those has 2 girls in it. Now you want to start some arguments, give this problem to anybody you know. It's true. This is the funnest problem in the world. And you can actually test this. You probably don't yet believe this, right? In other words, everybody thinks it's 1/2, but it's not. It's called the principle of restricted choice. And this is the way you solve this problem, is by listing all of the possible ways that 2 children can be born. Now, notice that if I walked into that same house and a child came out of the bedroom and the parent says, "This is our oldest child," and it's a girl, that changes everything. Because notice they say that this is our oldest child. Well, that means this one's eliminated. They weren't born boy first and then girl. If you're looking at the oldest child, girls had to be born first. Now what's the odds of the other child being a girl? 1/2. So what makes all the difference in the world, believe it or not, is whether you know whether that child is the oldest child or the youngest child. If you don't know, then the odds are 1 out of 3. If you know, whether it's the oldest or the youngest, doesn't matter. The odds are 1 out of 2. And if you go pick up any probability book, this problem will be in it. This is the classic probability problem. And I could not convince 13 relatives that I knew the right answer of it. Even though I'm a math major from School of Mines, nobody would believe me. It truly is funny. It's a great problem because it's an astounding result. And it's provable. How do you prove it? Go around your neighborhood, knock on the door, ask how many children they have, get a glimpse of one child without knowing whether it's the oldest child or the youngest child, and the data will prove that the odds of the other one being a girl are only 1 out of 3. And that's not based on the fact that if you have a girl, you're more likely to have a girl as a second child. That's based on it's 50-50 whenever you have a baby, whether it'll be a girl or a boy. In other words, we're talking independent events. Independence means there's no relationship between the two events. Dependence means there is a relationship. In other words, if it does rain today, well, it's more likely to rain tomorrow than otherwise. And in point of fact, when babies are born, if you do have a child of a certain gender, it is slightly more likely that your next child will be of the same gender. In other words, if your first child is a girl, it's maybe 51% likely that your next child will be a girl. But that's not what this probability problem is based on. This probability problem is based on it being 50-50 every time you have a child that it's a girl or a boy. If you're going to explain this to somebody, you need to write all 4 possible ways that 2 children can be born. And then the fact that you saw one of the children was a girl eliminates the boy-boy possibility. And now there's only 3 other possibilities, and only one of those has another girl in it. Cool, huh? Sam, you still there?
I'm here. Yeah, I'm here.
All right. Well, it's 5 o'clock, so I will let you go. But
thank you so much.
Yep, you're welcome. Talk to you next time.
Sounds good. Yeah, it was really helpful.
Incidentally, just a word. I have no problem doing 7:30 sessions, but really kind of need to know by the night before. Because what happens is, like, I might not wake up until 7:20, and I'm not in any space to do a tutoring session if I just find out about it at that point in time. If I know the night before, then I'll set my alarm clock and make sure I get up at 6:30 or something, and I'm ready to do a session by 7:30. Okay? So, like I said, I'm perfectly willing. You can't schedule it, but your mom can always text me. And the best way to reach me in the evening is with a text, not with an email. I might not check my emails that evening, but I'll always see my texts. So if she's looking for a 7:30 session, just have her send me a text the night before and say, can you do a 7:30 session tomorrow morning? And 95% of the time I'll be able to.
Sounds good, yeah.
All right, Sam. Have a good one. Talk to you later.